Okay, so hello and welcome to our video lecture for today. So this time we are going to discuss the Mahler-Breslau's principle, wherein the procedure is a simplified version of the combined tabular method and equilibrium method in establishing the influence line diagram for beams. So for our learning objectives, at the end of this module, you will be able to first derive the technique developed by Mahler-Breslau in establishing ILDs. Secondly, apply efficiently the technique developed by Mahler-Breslau, and after which we intend to appreciate the technique by making evaluative comparison to the previous methods to establish influence line diagram. So it was observed in our experience in ILD for reaction, shear, or moment that the procedure using the combined tabular method and the equilibrium method is quite tedious. So we do a lot of equations and tabulations and a sequence of calculations in order to establish our ILD. So this time, by and by, you will appreciate the method because comparing it to the previous one, it is so simple. So moving on to the fourth learning objective, we have evaluate the value of response function of various loadings using the influence line diagram. So we have actually establishing the influence line diagram using a unit load. What if that unit load will come into real loading like pointed loads that is not equal to 1 or a distributed load moving from one point to another. So bear in mind that your loading here is not fixed at any point, but rather it is moving from left to right along the beam. So before we proceed to the method itself, let us have a short biography of the discoverer of the method. So the full name of Mahler-Breslau is actually Heinrich Franz Bernhard Mahler. As a trivia, he was named as Mahler-Breslau to distinguish him from other people with similar names. And he was a German civil engineer and a high school teacher. He provided significant contributions to the theory of beams and frames in structural analysis. He was both a practicing engineer and theoretical researcher during his lifetime. He brought the previously separate elements of classical structural analysis together in a unified theory of beams and frames. He systematized the computational methods, in particular the principle of virtual displacements, and applied the energy sets systematically. He also calculated structures of airships. So as we can see, he has done a lot of legacy in structural analysis. That is why one of the principle in establishing ILD is the Mahler-Breslau principle. As a student, he helped fellow students of the School of Architecture with their revision of structural analysis and prepared them for the second state examination. Based on this teaching, he compiled his first textbook. So he has a lot of books, elementaries, handbook, their Festigets Layer. So elementary handbook of the strength of materials in 1875. So moving on, let us have this the types of influence line diagram. There are two types. So first we have qualitative ILD. So when we say qualitative, it only contains or present the slope without the ordinates. Okay, without the ordinates in it. And number two, the quantitative ILD or influence line diagram. So it shows the slope as well as the ordinates. So in our previous method, we have actually establishing the diagram after the numerical values. So from quantitative to qualitative. So this time, we are going to first establish the figure and then determine the ordinates. That is from qualitative to quantitative. So ILD for beam reactions made easy. So this is now the application of the Mahler-Breslau principle. So for support reaction, the procedure is that we just remove the restraint in the vertical direction. Introduce a unit displacement in the direction of reaction. Say we have here a simply supported beam. If we are concerned with the reaction or the ILD for reaction at A, all we need is to remove this one and replace it by a reaction that is free to move vertically, but it is restrained horizontally. So if we do that, we will be having a roller that is free to move downwards and upwards. We can see here in the figure. So at A, this was removed and then replaced by a roller that is moving up and down. And this is resting on this roller. So what we do is just to push it upwards at A. So since A is our concern, we'll just have to place 1 there, or the displaced value is 1. Okay. So at A, we place here the value 1, or the displacement here shall be equal to 1. Okay. So moving on, for ILD for beam shear, we will just have to make cut in the section and then introduce a unit relative translation at C. So when we say translation, if we are going to cut this, there will be a displacement on the left. Okay. See, this is the left portion. And the displacement at the right portion. So remember the just left and right of C. Okay. And then make this swing. Since we have a pin here, it will be displacing this way. Okay, so let us have a straight line here. So here it is. So remember that these two lines here, say this line and this two, are just parallel to each other. So as we can see, this section here is enclosed by two reactions, say pin and the roller here. So therefore, this is parallel. We can use the similar triangle. And if we are going to name this as delta 1, and this as delta 2, it will just yield to the total delta, which is equal to 1. So delta 1 has its corresponding rotation. Similarly, delta 2 will have its corresponding rotation. So basically, we will have an equation delta is equal to delta 1 plus delta 2. And from that, we will have the value of delta 2, say, if we label this as L1 and L2, say L1 and L2. Notice that L1 and L2 is within the boundary between these two support reactions. Since C here is in between these two support reactions, so L1 and L2 will be tagged as between, say if this is A and this is B, so L1 and L2 will be between A and B. And then by that, if we have a small deflection, remember that the tangent theta will be almost equal to the angle itself. So therefore, if we are concerned with theta here, we'll just have to multiply L1 and the angle. So therefore, we can say that delta 1 is equal to L2. To avoid confusion, perhaps we can interchange the notation here. So L1 will be on the side of 1 here, and L2 will be on the side of the 2 here, or theta 2, delta 2, and L2. So delta 1 will be equal to L1 times theta 1. Similarly, delta 2 will be equal to L2 theta 2. And since these two lines here, or the slope of the ILD for those deltas, so this one and this one, we can use ratio and proportion. So by ratio and proportion, we can see that delta 1 is to L1 and delta 2 is to L2. And then perhaps we can use delta 1 here, solve delta 1. Delta 1 is equal to delta 2 L1 all over L2. From this, we can have delta 1 plus delta 2 is equal to 1. Okay, this one, delta 1 plus delta 2 is equal to 1. So from this, we can just substitute this one. We have delta 2 L1 all over L2 plus delta 2 is equal to 1. And then we get the LCD. LCD is L2, so we'll just have to copy the first term. And then this is delta 2 times L2 is equal to 1. Okay, so by cross multiplication, we can cross multiply that one and then remain this as our left hand equation. We have delta 2 L1 plus delta 2 L2 is equal to L2. Hence, we can factor out delta 2, and what is left is L1 plus L2 is equal to L2. So finally, delta 2 will be equal to L2 all over L1 plus L2. So this will now be our concept. So actually, we do not need to memorize this one. Just bear in mind that these two slopes are parallel to each other and that is equal to 1. Just take a look at the triangle here. You can get it right. Say if we have delta 1, just get the length here, okay, and then divide it by the total length covered by the enclosure of these two reactions. That is actually L1 plus L2, okay, and then you can now use ratio and proportion. So if not, just stick to that formula. Delta 2 is equal to get the length, the base length of the triangle all over the sum of the two triangles. The sum of the bases of the two triangles, say L1 plus L2. And normally these two triangles are within the enclosure of the two support reactions. Okay, so that's it. If we know this delta 1 and delta 2, then it follows that we can obtain this one. Say this is delta 3 by ratio and proportion. So if this is L3, we'll just have to say that delta 3 is to L3, which is equal to this ratio, okay? Delta 1 over L1 or delta 2 all over L2. So if this is known, then we can right away get the other unknowns here. Okay? So that is the ILD for the beam shear. That is the procedure for Mahler-Breslau, and it is quite simple comparing to what we have done in the previous procedure. So next, we are done with the shear. So that is the procedure. We cut this one, and by the way, let us emphasize that the displacement of the left portion should always be negative, okay? And then the right portion should always be positive. And take note of the location of your pin connection and the roller support here. So just imagine that if you're going to push this up, the right portion, what will be the behavior of the beam? Of course, there will be a roller here resting on that, so it will still rest on this one. And if we have a pin connection tends to rotate this one, and it is restrained in one position. Okay, so do not displace this one because this is pin connected. It will just rotate. Okay, so if we push this downwards, the left portion, this will go up because this is pin connected at this point. So that is the Mahler-Breslau principle. And then for the ordinate, we have already introduced that we just get the base of this and then divide it by the whole base. Then we get this displacement here. So next, for the bending moment, we remove the ability to resist moment at C by using a hinge. So in short, we'll just have to place here a hinge support. Okay, so place there a hinge, and then we're gonna push this hinge upwards. Okay, introduce a unit relative rotation at C. So what will happen? So it will have this behavior. Okay, and there will be delta here. So here it is. So we apply here a pin connection and then push it upwards. So there developed here a delta. Okay, so we derive delta. So how delta is derived here? Say, if we are going to label our length, say this is L1 and L2. So there will be a corresponding rotation for that. Say this is theta 1 and this is theta 2. So let us name this as point C. So what will be the relationship here between this in order to determine our delta? So first, since we have a different rotation here, but the same delta, say this rotation is counterclockwise actually. So AC is a counterclockwise, and this rotation BC is clockwise. Thereby, the sum of the rotation will just be equal to 1. So theta here will just be equal to 1. And by rule of our trigonometry or geometry, isn't it that if we are going to bisect this one, this is also theta 2. And this is theta 1. Say this is horizontal line. So this is theta 2. This will also be theta 2. And this is theta 1. This shall also be theta 1. And the sum of the angles is equal to theta, which will be equal to the unit rotation. So if this is point C, and this has to be delta, say that is L1 and L2, okay, so we will just say that delta is L1 times theta 1 and delta will be equal to L2 theta 2. So equating delta to delta, we can say that L1 theta 1 is equal to L2 theta 2. Hence, we can use theta 1 will be equal to L2 theta 2 all over L1, and then we go back to this principle. Theta 1 plus theta 2 is equal to 1. So we substitute theta 1 here. L2 theta 2 all over L1 plus theta 2 is equal to 1. We can have the LCD, say L1. Just copy that one. So this is theta 2 L1 is equal to 1. By cross multiplication and factoring out theta 2 on the left side, what is left is L2 plus L1. So this must have to be cross multiplied by the right side. So L1. Therefore, theta 2 is equal to L1 all over L2 plus L1. Further, theta 2 could be expressed into delta because delta is our concern here. So from this equation, we have theta 2 is equal to delta all over L2. So we can replace this by delta all over L2. Thus, this is L1, L2 plus L1. Finally, this will cross multiply to the right side. So delta will just be equal to L1, L2 all over L1 plus L2. So we can actually interchange that one. So basically, if we are going to apply this one using this figure, delta is simply equal to, bear in mind that we multiply divided by sum, okay? The product all over sum. What is product all about? The product of the two distances and then the sum of the distances. So the delta here using this one, what is the product? L1 times L2. What is the sum? L1 plus L2. In this case, that is, if this is D, point D, it is simply AD times BD all over AD plus BD. So this is delta. And this is Mahler-Brest law for bending moment all about. And the procedure has made it easy. Okay, so if we know this, where your point of concern is, just take note of the reactions. Same true with the treatment we had with the roller and a hinge. Okay, so with regards to displacement. So if we have a pin here and the overhang here, for example, if we have to push this upwards, therefore it will just have an overhang length here. See? So that is the concept in application of the Mahler-Breslau. So that's it for the procedure. So this time we are going to have a revisit on the previous problem we had. So first, we are going to draw the ILD for the reaction at C. So we'll just have to draw here a line. Then we will let C to displaced by 1. Okay. And then this is pin connected. Remember that. So if we're going to push this beam upwards, then it will swing on your hinge. Hence, this will be your result. So we know this one, that is 1. We do not know yet this ordinate as well as this ordinate. So by the triangle, by similar triangle, we just have to ratio and proportion in order to determine y1 and y2. So the known variable here is the ordinate at this point. So we are going to utilize this triangle. And this triangle are similar to triangle y1 as the height and y2 as the height using those triangles. So we can say that y1, the base of y1 is 4 plus 1.5, that is actually 5.5, and ratio it by y2 is to 2. We're going to pair that by 1 is to 4. So therefore, if we are concerned with y1, we'll just have to pair it to 1/4. So y1, 5.5 will just transfer or cross multiply by 1. So that is 5.5 all over 4. So that will be equal to 1.375. So similarly, y2 will be paired on these given values. So 2 will cross multiply with 1 divided by 4, and obviously this is equal to 0.5. So by this week, this is now determined and y2 is determined immediately. Okay, so this is the solution for the reaction at C. How about the reaction at B? So let us work on that. So this time we are going to remove this hinge here and replace it by a roller that is moving up. So we push it upwards. So we take note of this location of your roller. So therefore, this will be the result of having B to be displaced by unit 1. So this will rise up, that is greater than 1. And of course, we still need to compute that one as well as this displacement. So again, we'll be utilizing here similar triangles. We can say that y1 is to 6 is equal to y2 is to 1.5. That will be equal to 1 all over 4. So therefore, y1 here will be paired to 1/4. That is equal to 6 divided by 4. Okay. which will yield to 1.5. So similarly, y2 will be paired to 1/4. So 1.5 will just be cross multiplied to 1. So therefore, y2 is 1.5 divided by 4. So that is equal to 0.375. So this is positive and y2 will be negative since it is below your zero line. So next is shear 4 meters from A. So first, we locate where is it. From A, we measure 4 meters, so it will bisect your 4 meters there. So as a rule, we are going to cut this one. Okay, we cut that portion. So after cutting, the left portion will go down and the right portion will go up. So as we can see, this delta here will not be necessarily equal to this delta here. So what is our criteria? What will be the larger value between this going down delta here and going up delta there? So just look at the span of it. Okay, so in this case it is actually symmetrical, wherein it is enclosed by your pin and the roller here. So basically this line should be equal. So that is how to determine that. So that will be equal because our criteria is project this, project that, and it has an equal leg or equal base for the triangle that will be formed out of this going downward and going upward, the deflection here. So we take note of the support reactions. Basically, we have a pin here and a roller at this point. So this is going down and that is going up for the right portion. And as a result, this will be pinned here. This will tend to go up. Although this is not pin connection, but it will rest on C and this will go down. So all of the values are not yet known. And by symmetry, we can say that this is just equal to 0.5. So anyway, I'll just show you that this y1 here and y2 will just be half of 1. Because remember that the delta here plus the delta at the bottom will just be equal to 1. And by symmetry, they are just equal. So we bisect 1 that is equal to 0.5. So anyway, we'll just show that it's y4. By ratio and proportion, just say that y1 is to 2 is equal to y2 is equal to 2, which is also equal to y3 is to 3. Sorry, y3 is to 2 also, and y4 is to 1.5. So basically y1, y2, and y3 are of equal values. So if we are concerned with the shear, is just equal to L1, okay, say this is the base of y1 is actually L2. So L2 all over L1 plus L2. Okay, so that is the principle. So if we have L2, L2 is just bisecting 4, so that is equal to 2. And this is equal to 2 plus 2. So that is actually 1 half or 0.5. So if we do this to our y2, will yield to the same value. And same value for y3, only y4 varies. So we just have to equate y4 is to 1.5 is equal to 0.5 all over 2. So any of these values. Therefore, y4 is 1.5 times 0.5 all over 2. So that is equal to 0.375. Okay, so that is for the shear at 4 meters from A. So next, we move to establishing the moment at 4 meters from A. And as for the procedure, we locate our point of concern 4 meters from A, that is here. So we place here the hinge and push it upwards. So we're gonna push that upwards. And of course, that will tend to move upwards by a certain delta. Okay? And this is pin connected here. And there will be a roller here. So if we're going to push that upwards, your left portion will just have a downward displacement at A, and it will remain at point B. So it will stay at point B. So similarly, at the other side, there will be a roller here. Therefore, this will be resting at the roller, pushing that upwards will tend for this displacement at B to go downwards. So we'll now compute for the values. So if I'm going to label this as y2 and this is y3, say we change that to y1, okay, so we denote delta by y1. So we are concerned with L1 and L2 here. So we know that delta is just equal to what? The product all over the sum. Okay, what product? Product of the length enclosed by these two, the various length that is enclosed by these two supports. And it so happened that L1 and L2 are equal because of symmetry. But it is not always the case. Okay, so the product of L1 and L2 all over the sum of L1 and L2. So basically, this is 2 times 2 all over 2 plus 2. Therefore, if this is 4, that is equal to 4 and it will yield to a delta equal to 1. So therefore, y1 is equal to 1. So by that, we can now have ratio and proportion y1 is 2. Perhaps we can use any side here, all over 2, and then equate it to y2 is to 1.5. So this is also similar to y3 is to 2. Hence, y3 here is obviously equal to 1. So y2 will be computed by pairing it to this, wherein y1 is 1. So we have 1.5 times 1 all over 2. So half of 1.5 is 0.75. And this is actually negative since it lies at the bottom. Okay, so I think we are done with the revisit on the procedure using the Mahler-Breslau method. Okay, and for the remaining problem, let us do this by Mahler-Breslau method. Okay, so it will be your activity for today. So this is the first problem. We are going to draw the influence line diagram for RE, shear at B, and moment at B using the Mahler-Breslau. First problem, and for the second problem, let us have this: a prop beam with a hinge somewhere 4 feet from A. So we are going to calculate reaction at A, reaction. So this is supposedly reaction at C. So this is reaction at C. And then moment 3 meters from A, and the shear 3 meters from A. So your answers shall be uploaded in the Google Classroom we will set. Okay, so this is for your activity for the day. So thank you for listening, and have more practice through that activity. So thank you.